Today, we're diving into a fascinating topic. Why don't whales get cancer? Most animals eventually develop cancer, but whales are a remarkable exception. So what's so special about whales that seems to protect them from cancer? And if we crack the code behind their immunity, could that breakthrough help us humans too? This mystery actually ties into a famous puzzle in biology called Peto's paradox. In this episode, we'll break down that paradox in detail. Welcome to Enigma Files. We all know that cancer is one of the deadliest foes facing humans today. Yet, many of us aren't entirely sure what cancer really is. So before we get to the heart of why whales don't get cancer, let's first explain what cancer is all about. Our bodies are made up of roughly 40 trillion cells. That's just an average, since taller or larger people have more cells while smaller folks have fewer. These cells work together nonstop to keep our bodies functioning and healthy. They're absolutely essential. But here's the twist. Our bodies have a built-in system that gives most cells a predetermined lifespan. When a cell reaches the end of its life, it simply dies. And not all cells live the same length of time. For instance, cells in the intestinal lining last only about 3 days, white blood cells around 9 days, and skin cells roughly a month. Brain cells, however, are a whole different story. They don't have a set lifespan, at least in theory. In short, every cell except brain cells has a built-in timer that eventually leads to its death. So, why do our cells have a built-in lifespan? The thinking is that as long as we're alive, these 40 trillion cells are working around the clock. Over time, all that nonstop work causes cells to age, malfunction, or even behave abnormally, sometimes even disrupting the work of healthy cells. To protect us from the damage that aging cells can cause, our bodies enforce a kind of expiration date on them. It's important to understand that a cell's lifespan is not like a human's lifespan. A cell is programmed to die at a certain time, regardless of whether it's in tip-top shape. It's almost like a built-in self-destruct mechanism. Now, you might be surprised to learn that every day about 400 billion cells in our bodies die. That's roughly 1% of all our cells, meaning around 300 million cells are dying every single minute. But don't worry, our bodies have a clever regeneration system. As cells near the end of their lifespan, they start dividing to produce a new, young clone of themselves. This fresh cell takes over the duties of its aging predecessor, which then dies off. Interestingly, while these two cells look identical, one is about to expire and the other is just starting its life. It's a bit like modern cloning. You can clone almost anything, but you can't clone a cell's lifespan. For example, if you clone an elderly person, you'd still end up with an elderly individual. To truly carry on, an old cell needs to produce a youthful, vibrant replacement. If you have watched the movie The Substance, you will have a profound experience of this. The new cell that's cloned takes over the work of the old one, while the old cell essentially commits suicide. This constant renewal mechanism is what keeps our body's total cell count steady at around 40 trillion, and it's crucial for maintaining our health. As I mentioned earlier, about 1% of our cells are replaced every day. That means in roughly 100 days, about 3 months, all of your cells have been swapped out. In a way, after 3 months, you're basically a clone of yourself. Think about it. After 3 months, you're not exactly the same person you were. You're a new version of you, a clone. The only exception? Your brain cells. They don't die off, which is why your brain isn't cloned. Since your memories and personality reside in your brain, you still feel like you're you. If your brain cells were also replaced, you might end up feeling like a completely different person. So, this mechanism is actually pretty clever. Now, consider that every day 400 billion cells die. This means there are 400 billion cell divisions happening daily. And during these divisions, there's always a small chance that something goes wrong, an error in the copying process that makes the new cell a little different from the original. When these mistakes occur, the faulty cell might not function like it's supposed to. There are a bunch of reasons why these errors might happen. For example, too much ultraviolet light hitting our skin cells can damage their genes, leading to errors in the cloning process. Viruses can also invade our cells. When they replicate, they might interfere with the cell's own copying process, causing it to fail. In short, there's always a risk of error during cell division. But here's the reassuring part. Our cells are equipped with self-repair mechanisms. If a cell spots an error after copying, it tries to fix it. Minor errors can be mended, and everything goes back to normal. However, if the mistake is too serious for the cell to repair, a built-in self-destruct program kicks in, and the cell dies, ensuring that these faulty cells don't hang around in our bodies. Now, this system seems almost perfect, but as with any system, there's a loophole. Errors can occur in the very part of the cell that controls the self-destruct mechanism. If that happens, the cell might lose its ability to commit suicide. This means you could end up with an immortal cell that won't self-destruct, even though it's not functioning properly. To prevent this from becoming a problem, our bodies have one last line of defense: the immune system. Every day, the immune system is on high alert, scanning for any cells that aren't behaving normally. If it detects a cell that's off and can't self-destruct, the immune system swoops in and gobbles it up, ensuring that no rogue cells remain in our body. However, even this final line of defense isn't foolproof. Sometimes, the immune system itself can slip up. Simply put, among these so-called immortal cells, there's a tiny chance that a defective cell pops up. This rogue cell can dodge the immune system. It won't commit suicide and nothing else can kill it. It basically becomes immortal. At first, an immortal cell might not seem too worrisome. It might just hang around in our body in small numbers without causing much trouble. The real issue arises when the cell still has the power to replicate. It starts to multiply, making copies of itself that are just as invincible, unable to self-destruct, and impervious to being killed. Soon enough, these cells multiply exponentially, and that runaway, ever-growing population of cells is what we call cancer. The one thing about cancer cells that's truly problematic is their unyielding nature. They don't die, and they replicate without limits. But why is this relentless replication so dangerous? Well, replication demands resources. As these cancer cells keep multiplying, they begin to steal the nutrients that normal cells need. Since the number of normal cells is fixed, as the cancer cells hog more and more nutrients, the healthy cells end up starving and eventually, the organs can't function properly. This scenario becomes life-threatening. Plus, if cancer cells break into the bloodstream or lymphatic system, they can travel throughout the body. And even in the blood, they might grow uncontrollably, potentially clogging blood vessels or lymph channels, which again poses a direct threat to life. So, the basic principle behind cancer is actually quite simple. A genetic mutation creates an immortal cell, and this cell keeps growing and replicating until it brings about the downfall of the organism. It's like an unstoppable weed in the garden. It continuously sucks up all the nutrients, eventually choking out the healthy plants. Given how simple the concept is, you might wonder why cancer is so hard to treat. The problem is that cancer cells are essentially our own cells. The only difference is that they become immortal. Because they are cells, it's really challenging for the immune system, and even for doctors, to detect them. They look just like the rest of our cells. Moreover, as cancer cells keep reproducing, they evolve and mutate, much like viruses. These mutations make it incredibly difficult for a single drug to wipe them out entirely, because they're always one step ahead in preventing a complete wipeout. With such built-in defense mechanisms, whether it's viruses or cancer cells, our best strategy so far is early detection. If we catch cancer before it mutates widely and spreads, it can be completely eradicated. But if it's discovered too late, then we're in deep trouble. Alright, we've given you a quick overview of what cancer cells are. Next, let's look at why whales don't get cancer. We have to start with the Peto paradox. The Peto paradox was first discovered and proposed in 1977 by the renowned British immunologist and statistician Richard Peto. While studying the rates of cancer in humans and other animals, he noticed something truly odd. Within a single species, say, among humans or even among all dogs, there's a trend. The incidence of cancer tends to be proportional to the size of the individual. Taller, larger-bodied people are more likely to develop cancer, while shorter, smaller ones have a lower risk. In 1998, a UK study tracked over 17,000 male civil servants for 25 years, carefully eliminating most external factors like smoking or drinking. They found a clear proportional link between height and cancer risk. Then, in 2011, another study in the UK followed over 1 million women and once again confirmed that taller individuals have a higher risk of developing cancer. This is actually pretty easy to understand. As I mentioned earlier, bigger bodies mean more cells. If the mutation rate is constant, then having more cells naturally increases the chance that one of them will turn cancerous. However, Richard Peto took a closer look at cancer rates across different species and uncovered something really bizarre. Whether it's mice, humans, elephants, or whales, each mammal's individual cell is roughly the same size. So, essentially, an animal's size just reflects how many cells it has. In fact, humans have about 1,000 times more cells than mice. And since humans live much longer than mice live for only 2 or 3 years while humans can live 70 to 80 years, about 30 times longer. A simple calculation would suggest that humans should develop cancer 30,000 times more often than mice. But guess what? The cancer rates are basically the same. And it doesn't stop there. Take whales, for example, the largest of all mammals. They have roughly 3 million times more cells than mice. Over a lifetime, a mouse and a whale experience about the same number of heartbeats, meaning their metabolic activity is similar. Purely based on cell numbers, whales should have a cancer risk 3 million times higher than that of mice. Yet, we don't see whales getting cancer, and elephants, too, seem almost immune. This oddity is what we call Peto's paradox. In other words, within a species, larger individuals tend to have a higher risk of cancer. But when you compare cross-species, that trend vanishes, and the bigger species often have a lower cancer rate. This phenomenon might hint at something crucial. The chance of a gene mutating into a cancer causing one might not be completely random. After Peto's paradox was introduced, many immunologists and medical researchers began rethinking the true nature of cancer development. Unfortunately, even over 40 years later, we still haven't found a definitive answer. But there are 3 leading hypotheses. Once you hear these 3 theories, you'll naturally understand why whales don't get cancer. And you might even get an idea of whether we can apply this whale example to help prevent cancer in humans. Stay tuned for our next video, where we'll dive into these 3 hypotheses in detail. If you enjoyed this video, don't forget to give it a thumbs up, subscribe, and turn on the notification bell. It really means a lot to me. Your support is my biggest motivation to keep creating. Thank you, and see you in the next one.